Alright guys, I know this video is late, my bad, I had things to do. So, go ahead and sketch your figure below. Boom. Now draw another figure that has the same exact shape, but a different size. Oops. Same shape, different size. What did that remind you of? Similarity. Good. Remember, congruent was same shape, same size. Similar is going to be same shape, different size. So here's some examples. All these triangles are similar to, and we're going to learn that these were dilated. This being the original, it either got smaller or bigger. Okay, we're going to talk about that today. Again, here's your standard, SRT, talking about dilation, etc., etc. So, how can I understand dilation and scale factors? What happens when you go to the eye doctor and she dilates the pupils of your eyes? For those of us who went to the eye doctor lately, that's right, they get bigger or smaller. The size changes. Shape stays the same. Okay, regular pupil, dilated pupil. Look how big that is. Pretty big eyes. So, here's a shot of my pretty blue eyes. And this is me when I get angry. You know, a little red around the eyes. We're going to talk about scale factor. Is the number that describes how many times larger or smaller the copy is than the original image. How many times wider is the pupil on the right than the pupil on the left? Let's take our handy dandy ruler. I'll hold it up to this pupil. That's about 1 centimeter, give or take. Come over here, and that Skeeter's 2. So we're going to say it's twice as big. Its scale factor is a 2. So, the sides of the blue triangle are how many times larger than the red triangle? Let's count. So we got 1, 2. Here, let's use my marker here. 2 for red. And blue, let's see, 1, 2, 3, 4. Well, 2 times 2 is 4, so blue is going to be twice as big. How can you tell? What's the scale factor? Well, we're timesing 2. Let me change my color here. We're timesing 2 every time. 4, 4, 4 root 2. Everything's being scaled up by 2. Multiplying the original length by the scale factor will give you the length of that part of the copy. So, scale factor 2. I know this sounds easy because it is. So, some vocabulary. The original figure is called the preimage. The copy is called the image. Okay? When a point like A is translated, we call the translated point A prime. Not Optimus Prime, just A prime. Okay? So, A preimage, blue image. After the dilation. So, if the scale factor is bigger than 1, the image is bigger than its preimage. So, as you can see, red is the preimage, blue is the image. The sides of the blue square are twice as long as the sides of the red square. So the scale factor is 2. And again, if we were just counting the top here, 1, 2, 1, 2, 3, 4, scaled up by 2 times 2. Okay? And that applies to all the sides. If the scale factor is between 0 and 1, notice no negatives, so either going to be 0 to 1 or anything greater than 1, and obviously that means 1 doesn't change anything. The image is smaller than the preimage, so this time red is our preimage, blue is our image. So this is going to be 2 and 1. So we went from 2 to 1. That means we took half of it. That's right. Okay? Okay. So it's going to matter. Less than 1 gets smaller. Greater than 1 gets bigger. Okay? So, parts of the dilated figure. Let's see here. Parts of the dilated figure may move, but the center of dilation does not move. The center of dilation for this triangle is going to be 0, 0. What happens as it expands and shrinks? Let's find out. This triangle's not working, guys. Alright, here we go. So, watch the triangle. If we scaled it up, notice the sides did not move, they just got longer. But this blue line, notice it, it's moving, isn't it? This blue line's not going through the center dilation, so it's going to move. And as we get smaller, notice, again, it moved, but these red lines just get shorter. They're still kind of in the same spot. You could say that blue line here, whenever you dilate it, is always going to be parallel to the original. So, the side that does not go through the center of dilation changes positions, but is always parallel to the original position. Whoops, I'm trying to get my marker here. Always parallel, okay? And the sides that go through the center do not change. See my font here, red, does not change. Blue will be parallel to the original. So important ideas. A dilation leaves a segment passing through the center of dilation in the same position and takes a segment not passing through the center of dilation to a parallel position. Good stuff. So, the center of dilation for this triangle is at point A, right here, negative 2, 1. Which sides will keep their same position? Which sides will move to the parallel position? Well, we're just going to go with colors. That's right. Red, even though I'm using a blue pen, so why don't I just make that color coordinated? Red is going to keep the same position. Parallel is going to be the blue one. And hopefully, my little triangle's working. And indeed, you're right. Okay. Let's move on. So, the center dilation of the triangle is negative 2, 1, again, right here. If the triangle is dilated by a scale factor of 2, where would points A prime, B prime, C prime be located? So, scale factor by 2. We know it's going to get bigger. Okay. We're going to count this side. 1, 2, 3. So if it's getting bigger, we decide to times everything by 2. 3 times 2 is 6. Okay, so I'm going to take my triangle here. In fact, let me just go ahead and put a little dot here. I know it should be 6 long, so 1, 2, 3. I'm counting from A. 1, 2, 3, 4, 5, 6. B prime should be right there. So I'm going to grab my triangle. I'm going to dilate it as so. A little too much. There we go. Boom. So here's B prime. C prime's down here. Notice A prime stays put because it's the center of dilation. And as you can see, everything's scaled up. So they want the points A. Let's see, I think I have on my other slide. Nope. So A prime stays put, so negative 2, 1. B prime, let's see, 1, 2, 3, 4, 1. So 4, 1. Excuse me. C, 1, 2, 3, 4. So that's 4 again. I'm going to go down. 1, 2, 3, 4, 5. Negative 5. Sounds good? This is just a counting game, okay? Count. Count, 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 count. And notice it's still the same shape, but different size. 1/3. Now, we know for a fact that means it's going to shrink. Our image should be smaller. So, again, if we have 3 here, 1, 2, 3, we know it's going to shrink by 1/3. So, what's 1/3 times 3? 1. So it should be 1 block wide. So I'm going to take my triangle here, shrink her down. So indeed, it did get smaller. And they want the new coordinates. So again, this did not move because it's the center of dilation. B, on the other hand, and let's get this giant 3 out of the way. Because now this is B prime. This is C prime. So B prime is back 1, up 1. So negative 1, 1. C prime, negative 1, 0. Boom. Easy peasy. So, the center dilation for this triangle is at C, negative 4, 5. Which ones will keep their position? Which ones will be parallel? I'm just going to kind of make this video short and sweet. So, that's right. Anything going through the center dilation is going to keep the same position. Okay? AB, on the other hand, this one's going to move. If we do a scale factor of 3, it's going to get bigger. Oops. It's going to get bigger. So again, just count 1, 2, 3. 3 times 3 is 6. So 1, 2, 3, 4, 5, 6. Same thing this direction. 1, 2, 3. So 1, 2, 3, 4, 5, 6. And it's going to get bigger. Really, when it comes to these things, I would just try to make sure we stick with those rules. Scale factor 3 should get bigger. If it's less than 1, should get smaller. My end result is bigger, so that means I'm on the right track. Center dilation is negative 5, 5. That's right here. So, again, these sides will not move. Okay. This AC will move. In fact, it should go in. I think it's 1. I think I put a small scale factor for this one. I did. It's going to go in by half. Okay? So real quickly, let's count this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Half of 10 is 5. So 1, 2, 3, 4, 5. That's C prime. I'm going to go straight down and connect the dot. Connect the sides. Because I know this whole thing, half of it's going to be right here. Because remember, it keeps the same shape. Don't go through the work of trying to count this. And even if you did, look. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 again. 10 total. Half of 10 is 5. I counted diagonals. Don't think it's the same distance here. Those diagonals are just a little bit longer. But hey, same shape, and it shrank because of it being half. Should be smaller. Now, what happens if center dilation is at the origin? Scale factor is half. Stick with the rules. Half means it's going to get smaller. Okay? Alright, I don't have the end result. It's going to get smaller. So, I just counted this was 5 a second ago. Half of 5 is 2.5. So B prime should be right here. I'm going to come over here to A. Again, that's 5. Half of that will be 2.5. So that's going to be about right there. And C, well, let's face it, C is going to meet them in the middle anyway. Because remember, same shape. So C is going to be right here. Okay? My new triangle did get smaller, like we said it should. And they want the coordinates. Well, let me show you something. A, B, C. When the center dilation is at 0, 0, all you do is multiply by the scale factor. So let's get the original points real quick. What was that? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's 5, negative 5. I think B is negative 5, 5. C is 5, 5. So I'm going to times all of this by 1/2. And you'll find out we get the points I just counted out. What I'm trying to tell you, there's a number of ways to figure out these new points. But when it comes to the center dilation being at the origin, all you do is multiply by the scale factor. So 5 times 1/2, that's 2.5. Times the negative, well, that'd be negative 2.5. And I think you already got the drift here. All of these are going to be cut down by half. And if you go back and look, C is indeed 1, 2, half, up 1, 2, half. Okay? Remember, don't confuse these things. Back here, we were counting. Okay? We were counting with these. Center dilation is at 0, 0. So you multiply. That's your shortcut. Another important idea when center dilation is at the origin, to find the vertices of the image, just multiply the coordinates of the vertex by the preimage with the scale factor. Example, if we have 3, -9 for point A, and dilated with the scale factor 1/3, with center dilation at the origin, remember origin is 0, 0, then A prime will be 1/3 those points. So 3 times 1/3 is 1, and -9 times 1/3 is -3. Simple, simple. Let's see here. Using the coordinates on the grid, draw a rectangle. Boom. Using the coordinates for the preimage, find, let me see, is it the right thing? 0, 0, 0, 2. Alright, good. So there's your coordinate. So if we dilate by a scale factor of 3, with the center dilation at the origin, that means all you do is times every single one of these points by 3. You'll get your new points. So 3, 3, 0, 0, 6. 3 times 1 is 3. 3 times 2 is 6. 3 again, 0. And boom. See? Just multiply the coordinates of each vertex by the scale factor. We did that. But only if the center dilation is at 0, 0. Don't confuse these properties. And again, it did get bigger because our scale factor was 3. And if it was less than 1, it should get smaller. Okay? So, here's a new example. Have your coordinate points. Center dilation again is at 0. Notice something here. None of the sides go through the center dilation, which means the whole triangle is going to move as far as these sides go. Okay? So, if our scale factor is 2, it should get bigger. Okay? And since I already know my tricks, center dilation is at 0, all you got to do is times every one of these by 2. 2 times 0 is 0. 2 times -2 is -4. And 2 times -4 is -8. 0 again. And those would be -8, -8. Let's check our work. Skadoosh. It went off the graph a little bit, but hey, I got the right answers. Because all you have to do is multiply when the center dilation is at the origin. And again, notice, these lines are parallel to the image. I'll put little 2 arrows so we can distinguish. Okay? That's an important feature to remember. Okay? Cool. So again, using coordinates of the preimage, find the coordinates of the image if we dilate by a scale factor of 2 with the center dilation at the origin. If you want, go ahead and pause the video, see what you get. Just remember, all of it's going to move because none of it's going through the center dilation, so just times it by 2. Yes, it should get bigger, and it did. Okay? Looking good. So, let's dilate the rectangle scale factor 2. Center dilation is -3, -1. So you just count. It is going to get bigger because it's greater than 1, but this is your center dilation. This side and this side's not going to move. This side and this side will, but just count. You got 1 here, 2 here, times those, so count 1, 2, 1, 2, 3, 4. Kind of missed it. There we go. But you're right, it should get bigger. Okay? That's pretty much the gist of dilations. This is just more practice. Copy it. Center dilation is at the origin. 3/2. Ask yourself, is 3 over 2 greater than 1? Yes, yes it is. That means it should get bigger. Okay? So, did all the sides grow by the same amount? No, they all grew by the same ratio. Same ratio. That's the important part about similar polygons, okay? We'll get into that later. Let's see, the length of one preimage side was 4. What is 2/3 times 4? I think I got that backwards, guys. 2/3, 3/2. Whoopsie daisy. Let's see here. Did I, you can only find the lengths of the sides of an image, multiply the length of the corresponding sides. Preimage. Yeah. Yikes, guys. I kind of messed that up. Let's see. Oh, wait. I was working backwards, wasn't I? Oh, yeah. I was working backwards. Anyway, just forget about that. So if I have triangle def is a 3/4 scale dilation of triangle ABC. So it got smaller because 3/4 is less than 1. If the distance from A to C is 19.1, what is the distance from D to F? Whoops. So, let's take your 19.1. That's the original. Wait. Triangle def is a 3/4 scale dilation of the triangle ABC. If the distance from A to C is 19.1, what is the distance from D to F? Scale dilation. So, the blue one is our image. Okay. We're applying the scale factor. So I'm going to multiply this by 3/4. And that should give us our answer. So if you get your calculator, 19.1 times 3 over 4, we get, 14.325. Okay. So, and really the idea behind this is that your, let's see, how can we say this? Your preimage times your scale factor is going to get you your image. Okay? And since this is just length, it's all in one dimension, so you can get away with stuff like this. When we talk about area, that's a whole different thing, and we'll get into that later. So, model railroad setup represents a 1/32nd scale copy of a real train. If the model boxcar is 10 inches long, how long is the life-sized boxcar? Okay, this is almost like your Hot Wheels or Matchbox cars. So the setup behind this is you take your original size, scale factor, and then your model size. It will equal your model size because it's scaling it down. We don't know what the original size is, so that's X. We do know they applied a 1/32nd scale factor, so simply solving for X, so to make this jump, we times both sides by 32. So these would cancel. This dot's a little low, supposed to be right there. So 32 times 10 gets 320. This is in inches, but if we did the conversion to feet, we get 26 feet, 8 inches. That's pretty realistic for a life-size train car. Okay? Let's keep going. Now, let's see. We're just talking about sides of a pentagon. They all measure 5 units. It is dilated to create the new pentagon, which is VWXYZ, with the sides all measuring 9 units. What is the scale factor? Well, again, your original times the scale factor equals the new image. We're dividing by 5 so we can solve for S, and we get our scale factor. Okay? So going back to this idea with this model train, This is a good formula to keep in mind. Original size times scale factor equals, instead of model size, we can say maybe image size, you know, the after. So keep all this in mind if you want to take some good notes. Let's see. In the dilation to the right, EB would become the new segment. What can you tell me about those two segments? Well, they're parallel. Good. And that scale factor, see, it popped right back up again. That scale factor is going to be true for these because length is a one-dimensional thing. Every one of these is going to be 9/5. They're going to keep that same ratio. And as always, it didn't go through the center dilation, so it's going to be parallel. All these are parallel to each other. Okay? And I think, let me see here. Same shape, different size. See how that's coming back? There's going to be similar figures. And look, new symbol right there. Just the squiggly worm. Okay? No equal sign underneath it. That means similar to. We're going to skip that. Skip all that. And here's your homework. I think a lot of you already started working on it, and the answer key is already up. So, you have a good night. I'm going to leave you with Christopher Walken. I got a fever, and the only prescription is Mocabo. All right, good night.